Today we will lecture 10-1 on the natural response of RC circuits. The objective of today's lecture is to find the natural response of a first-order system or an RC circuit, which can be described by a first-order differential equation. This will involve finding the initial voltage across the capacitor, the time constant for the first-order circuit, as well as the final value, and finding currents and other values and making a sketch. Recall that the natural response for a first-order circuit is when an inductor or capacitor is connected to a DC source and is suddenly disconnected, and the stored energy is released into a resistive network. Next lecture, we will talk about the step response, which is when a DC source is suddenly connected to a capacitor or an inductor and it begins to store energy. The third method of analysis for these problems is a general solution equation, which we will also talk about during next lecture. Since RC circuits can be described by a differential equation, let's derive a general equation for the natural response for an RC circuit. So here we have an RC circuit with a resistor in parallel with a capacitor. We're going to use KCL in order to analyze this to derive that equation. So what we get is that IC plus IR equals 0, or in terms of the voltage across the capacitor, we can write this as C dV dt plus V over R equals 0. So rearranging these equations, I can write C dV dt is equal to negative V over R, or dV over V equals negative 1 over RC dt. And that's our equation using separation of variables. So the way to solve this problem is to integrate both sides of the equation from 0 to t. So the integral from 0 to t, dv over v, equals the integral from 0 to t, negative 1 over rc dt. So we have the natural log of v of t over v of 0 equals negative 1 over rc t. In order to get rid of the natural log, we raise both sides of the equation to the e. So we get e to the natural log of v of t over v of 0 equals e to the negative 1 over rc t. So we have v of t over v of 0 equals e to the negative 1 over rc t. And finally, v of t equals v of 0 e to the negative 1 over rct. Note that tau, the time constant for an RC circuit, is tau is equal to R times C. So this can also be written as V of t equals V of 0 e to the negative t over tau. So you notice that this looks very similar to the equation for the natural response for an RL circuit for an inductor, except we've replaced all the currents. So it has all duals for these very reasons that their equations are very similar, except one is voltage because capacitors store energy in the form of, the other is current because inductors store energy in the form of current. Similarly, just like the voltage for a capacitor is continuous for all time, the current through an inductor is also continuous for all time, although the current for a capacitor can abruptly change from a positive to a negative number based upon whether the capacitor is storing or releasing energy. Recall that under DC conditions, the capacitor looks like an open circuit, so if we're talking about an equals 0 minus, the current through the capacitor would be 0 amps, modeled by a circuit. Then, since we have a capacitor in parallel with a resistor, we can use Ohm's law to find the current resistor, or the voltage across the resistor, where V naught over R is equal to IR because the current through the capacitor relates to the first derivative. And you see here that we have a graph of the voltage, V naught e to the negative t over tau, where it drops to 0.3 V naught in one time constant, and for 5 time constants, we would essentially say it is totally discharged. Now notice that we have a discontinuous signal for the current, because it starts at 0, and then once the cap starts discharging, the current through the resistor spikes up to V naught over R and then dies off to. And the current through the capacitor would be very similar, except it would go down to negative V naught over R and then start discharging. The power dissipated is based upon the equation for the power for a resistor, P equals I squared times R. And remember that P is equal to dWd. So you can integrate the power to get the energy, which is how we get the second equation. And that yields 1/2 CV naught squared joules. So the analysis for an RC circuit is very similar to what we did for the RL circuit. We find the voltage V0 across the capacitor. We find the time constant of the circuit, tau equal R Thevenin, or R equivalent times C, and then use the expression V of t equals V0 e to the negative t over tau. Okay, so let's try example 1, U of minus t amps. So here we have a current source that is 1 amp before time 0, and it turns off at time 0. So to solve this problem, we're going to draw the circuit at t equals 0 minus, DC steady state conditions, the cap looks like an open circuit, and t equals 0 plus. We use this circuit to find tau equal to R Thevenin times C. So here we have 1 amp, 10 ohms, 20 ohms, and the open circuit to represent the capacitor, and that's VC of 0. What you should note here is that the 20 ohm resistor is an open circuit, so there's no current flow. So the voltage across VC of 0 is the same as the voltage across that 10 ohm resistor, which is 10 times 1, or 10 volts. For tau, the current source is open because it's now off, and I have a 10 ohm resistor here, a 20 ohm resistor here, and a capacitor that is 0.1 farads. So this capacitor sees the 10 and 20 in series. So R Thevenin equals 10 plus 20, which equals 30 ohms. And tau is equal to 30 times 0.1, which is 3 seconds. Finally, VC of t equals VC of 0, 10 e to the negative t over 3 volts for t greater than or equal to 0. The current through the capacitor is C dV dt, so that would be 0.1 times negative 10 over 3 e to the negative t over 3 amps, so that would be negative 1/3 e to the negative t over 3 amps for the current through the capacitor. VR of t is the voltage across that resistor. So that's going to be 20 IC plus the voltage across the capacitor. So that's going to equal negative 20 over 3 e to the negative t over 3 plus 10 e to the negative t over 3. So that's 30 over 3 minus over 3. So that is 10 over 3 e to the negative t over 3 volts. And then finally, we find the current through that resistor, and that is VRT over 10, which is 1 over 3 e to the negative t over 3 amps. Okay, let's make a sketch of the voltage. So here we have VC of t on the vertical axis, and we have time on the horizontal axis. So the initial voltage for the cap is 10 volts, and then it dies off to 0 in 5 time constants, or 15 seconds. Now let's sketch the current for the capacitor. The current for the capacitor, time in seconds in the vertical axis, is the current in amps, is initially 0 amps, and then right after t equals 0, the current for the capacitor jumps down to negative 1/3, and then it dies off to 0 in 15 seconds. The initial voltage for the 10 ohm resistor, VR of t, is also 10 amps. But then what happens right after time 0, it immediately jumps down to 3.33 volts. And then it dies off from there. And that's based upon this equation, 10/3 e to the negative t over 3. Now, what about the current for the resistor? The current for the resistor is initially 1 amp based upon this circuit here. So this is IR of T. So it's at 1 amp. And then it immediately jumps down to 1/3 and dies off. So it goes down here to 1/3 and it then dies off to 0. Now let's look at example 2. We have an RC circuit where the switch opens at time 0. Determine the voltage across and current through the capacitor for t greater than or equal to 0. Also create a sketch of the voltage and the current. So at t equals 0 minus, the switch is closed and we have DC steady state conditions. At t equals 0 plus, the switch is open and we use this circuit to find tau equal R Thevenin times C. And we use this circuit to find VC of 0. And we can also find IC of 0. So we have 24 volts, 10 kilo ohms, 2 kilo ohms, an open circuit for the capacitor. So VC of 0 is the voltage divider, so it's 2 over 12 times 24, or VC of 0 is 4 volts. IC of 0, since it's an open circuit, is 0 amps. Draw the circuit again with the switch open. So I have 2 kilo ohms in parallel with 40 microfarads. So tau is equal to R Thevenin times C, or tau is equal to 2K times 40 micro. So tau is equal to 80 milliseconds. So VC of T is equal to 4 e to the negative 12.5 t volts. And that's for t greater than or equal to 0. And IC of t is equal to C dVC of t dt, which is equal to negative 2 e to the negative 12.5 t milliamps. And that's for t greater than or equal to 0. So our sketch of the voltage first, there's the time in seconds, VC of t in volts. So it starts at 4 volts. And it dies off to 0 in 5 time constants, or 0.4 seconds. Finally, time in seconds, IC of t in amps. As we found here, it starts out at 0. And then as soon as the discharging starts, it jumps down to negative 2. And then it dies off to 0 in 5 time constants. Now let's look at example 3. For the following circuit, assume the operational amplifier is ideal and the capacitor is initially uncharged. Use KCL to derive the output V0 of t. What type of op amp is it? If the input is VG of t, sketch the output V0 of t. So since the capacitor is initially uncharged, we know that the initial voltage across it is 0. So what we're most interested in is what happens after the switch closes. So when the switch closes, that will be t equal 0 plus. So the first thing you should notice is that current does not flow into the op amp. So if the current goes through the capacitor, if we label that IC, IC is the same as the current that goes through the 80 kilo ohm resistor. Next, we're going to write a KCL equation at the negative terminal. Now recall that if the positive terminal is connected to 0 volts, then the negative terminal is connected to 0 volts. So the KCL equation is that VG over 80K is equal to negative 250 nano dV0 dt. Negative 250 nano dV0 dt. So VG is equal to negative 20 milli d v naught dt. And if we solve this equation for v naught of t, we get that v naught of t is equal to the integral from 0 to t negative 50 vg of t dt. So the answer to the question about what type of op-amp we have here, this op-amp is an integrator. It takes the integral of the input, Vg of t, and multiplies it by negative 50. So now, let's figure out what that would be for the circuit that we have here. The first thing you should notice is that Vg of t is equal to 75 millivolts between 0 and 2 seconds. And it's equal to negative 75 millivolts between 2 and 4 seconds. So V naught of t is equal to the integral from 0 to t, 75 milli times negative 50 dt, and that's between 0 and 2 seconds. And it's equal to the integral from t to 2 times negative 75 milli times negative 50 dt plus the voltage V naught at 2 seconds, and that's between 2 and 4 seconds. So V naught of t is equal to negative 3.75 t volts between 0 and 2 seconds, and it's equal to 3.75 t minus 15 volts between 2 and 4 seconds. So the last thing we have to do is to create a sketch. So the vertical axis is V naught of t in volts, and the horizontal axis is the time in seconds. And so what we have from 0 to 2 seconds, we have a line that decreases with a slope of negative 3.75. So it goes to negative 7.5. And then between 2 and 4 seconds, we have a line that increases with a slope of 3.75 that stops at the 0. And this concludes example 3. For the following circuit, assume the operational amplifier is ideal and the capacitor is initially uncharged. Use KCL to derive the output V naught of t. What type of op-amp is it? If the input is Vg of t, sketch the output V naught of t. So once again, since the capacitor is initially uncharged, we know that Vc of 0 is 0. So now, let's close the switch at t equals 0 plus. And once again, we want to write the KCL equation for this circuit, recalling that the current through the capacitor is the same as the current through the 1 kilo ohm resistor. So we will have 800 pico dVg dt equals negative V naught over 1K. That's our KCL equation. So now, if we solve this equation for V naught, we get that V naught of t is equal to negative 800 nano dVg of t dt. So here we have a differentiator. So finding the derivative of a waveform is the same as finding the slope of the tangent line. So looking at the lines we have here, we see that the slope of this first line is 2 volts per microsecond. The slope of the second line is negative 2 volts per microsecond. And the slope of this third line is positive 2 volts per microsecond. So V naught of t is equal to negative 800 nano times 2 volts per microsecond for the interval between 0 and 1 microsecond. And we see that V naught of t is equal to negative 800 nano times negative 2 volts per microsecond for the equation between 1 and 3 microseconds, and V naught of t is equal to negative 800 nano times 2 volts per microsecond for the region between 3 and 4 microseconds. So V naught of t is equal to negative 1.6 volts between 0 and 1 microsecond. It's equal to positive 1.6 volts between 3 microseconds, and negative 1.6 volts between 3 and 4 microseconds. So if we make a sketch, the horizontal axis is the time in seconds. The vertical axis is V naught of t in volts. So between 0 and 1, 1 and 3, and 3 and 4. Between 0 and 1, we have negative 1.6. Between 1 and 3, we have positive 1.6. Between 3 and 4, we have negative 1.6 again, and then the line goes back to 0. And this concludes today's lecture on the natural response of RC circuits.